In this video, we're going to solve trigonometric equations and inequalities. Now, a conditional equation is an equation that has at least one solution, but it is not an identity, so that's what we're going to be working with, our conditional equations. We're going to start with something simple. We're going to start with a cosine of x is equal to some number a, where, of course, that the range of cosine is between -1 and 1. So, we have to have the cosine of x is equal to some number between -1 and 1. And I have these two examples. We have to pay attention to the directions. Now, the directions say I want for all real numbers, not in a particular interval. So what I'm going to do is I'm going to go out and first of all, before I get my calculator out, is I'm going to go see if these are on the unit circle. If they're on the unit circle, it is likely I'm going to be finding exact answers. Now, this one doesn't tell me to use degrees or radians, so I'll do one in degrees and one in radians. Then I'm going to find the x, the angle that's going to satisfy this. If they want exact, and it will say find all exact, then I will give exact values, and I'm not going to use my calculator. If it doesn't say exact, which we'll do later, I'm going to use my calculator, and we'll do it that way. So I go on my unit circle, and I look to see where the cosine or the x value is equal to the negative square root of 3 over 2. That happens right here, and it happens right here. Oh, not right there, right here. So those are the two locations in which the cosine of the angle is equal to negative square root of 3 over 2. So again, I'm going to do this first in radians, and I'll do it in the second one in degrees, because it didn't say. So that tells me that x is equal to 5 pi over 6 plus 2 pi k, or x is equal to 7 pi over 6, 7 pi over 6 plus 2 pi k. You're probably thinking, why did I add on that plus 2 pi k? Well, cosine has a period of 2 pi k, and so any angle that is coterminal to 5 pi over 6 or 7 pi over 6 is going to satisfy the cosine of x is equal to negative square root of 3 over 2. So I have to add that on because they want all real numbers. And they didn't say exact, but I'm going to say exact for this one, for this example. So then for the second one, I'm looking for the cosine of x is equal to the square root of 2 over 2. This time I'm going to use degrees. So that happens on this angle, and it happens on this angle. So x is equal to 315 degrees plus 360k, because anything coterminal to 315 will give me the exact same answer when I do take the cosine of that angle. Or x is equal to pi over 4, which is 45 degrees, plus 360k. Now I only add these when I'm asked to find all real numbers. If I am looking for an answer in the interval, then I'm going to only answer in the interval. I'm not going to find coterminal angles that will satisfy that solution. Here's a summary for solving the cosine of x is equal to some ratio. And the solution set, when it's 1, obviously it's going to be 2 pi and multiples of 2 pi. So 2 pi, 4 pi, 6 pi, 8 pi. If it's 0, then I am going to be straight up. So this would be pi over 2, not 2 over pi. So pi over 2 plus pi k. So pi over 2 and 3 pi over 2. If it is a -1, then I have x is equal to pi plus multiple 2 pi k. So 3 pi, 5 pi, 7 pi, all the odd multiples. If my ratio is bigger than 1 or less than -1, then that equation that I have, the cosine of x is equal to a, has no solution. I'm going to do something similar with the sine. So once again, I want all real, I want it exact. So I'm going to just shove that in there, exact. I'm going to do the first one in radians and the second one in degrees. It doesn't tell me, but if it did, I would know how to do it. So again, I get my unit circle out. And I'm going to look on my unit circle where the sine, or the y value, is equal to negative square root of 3 over 2. So this angle and this angle. So when x is equal to 4 pi over 3 plus, and you're right, 2 pi k, the coterminal angles, and when x is equal to 5 pi over 3 plus 2 pi k, all of those coterminal angles. Now I'm going to do the next equation in which I'm asked for the negative square root of 2 over 2. That happens at 210 degrees. And it also happens, not 210, my apologies, it happens at 225 degrees, and it also happens at 350 degrees. So when x is equal to 225 degrees plus all coterminal angles, and when x is equal to 315 degrees plus all coterminal angles. And again, here's the summary for solving the sine of A. We're going to do the same thing for the tangent. And I'm going to write exact. Once again, I'm going to do it first with degrees, and then radians, and then I'm going to do it with the degrees. Bring my unit circle back in. So I'm looking for the ratio in which the y value over the x value on the unit circle is equal to a negative square root of 3 over 2. And that's going to happen when I'm at 2 pi over 3 and when I'm at 5 pi over 3. So x is equal to 2 pi over 3 plus its coterminal angle. And when x is equal to 5 pi over 3 plus its coterminal angle. Now the thing about tangent is that I can write it like this and it's totally right. But I also can combine these because I realize the difference between 5 pi over 3 and 2 pi over 3 is a difference of pi. I've got a difference of pi between those two. So I can combine this into 2 pi over 3 plus just pi k. And that's also because the tangent has a period of pi. So they're not necessarily coterminal now, but we do know because tangent has a period of pi, I can combine these into a single solution. I'm going to do the next one in degrees. So I'm looking for where the tangent is equal to 1. The tangent is equal to 1 is when the x and y are the exact same values and the exact same sides. So it happens at 45 or 225. So I can do x is equal to 45 degrees plus 360k, and x is equal to 225 plus 360k. Now the thing is, I can also combine these, and I can just say when x is equal to 45 degrees plus 180 degrees k, and that would work as well. It's okay to write them separately. It's not wrong. It's just nice if we can combine it into a single solution like that. So here's some problem solving for trig equations when they're very basic. We always want to isolate the trig function if we can. There are times, however, in which we won't be able to, and that means it's going to look something like a quadratic. So I started out with something fairly straightforward, and now let's pay attention to these next couple of problems. They're going to be similar, but they're not exactly the same. Now I'm going to pay attention to my interval. I'm going to find all real numbers in a particular interval, and the interval is given in radians. So that tells me that my answers are going to be in radians, and they're also telling me to leave my answers in pi. So that's the same thing as saying I want exact. So once again, I'm going to go out to my unit circle, and I'm going to see where on my unit circle the cosine, or the x value, is equal to a positive 1/2 in radians. So the cosine is equal to a positive 1/2 at pi thirds. So pi over 3, and I'm just going to erase this and move it over because I need a little bit of space. So pi thirds plus 2 pi k. And you're like, but wait a minute, she said it's an interval. Yeah, I did. Give me just a moment. And the other location is at 5 pi over 3. 5 pi over 3 plus 2 pi k. Unlike my previous example where I just had a single angle x, I said x is equal to and I'm done. In this case, I've got x over 2 is equal to. I got to set this angle, which happens to be x over 2, not just x, equal to that solution. Now, to find the solution, I'm going to have to multiply by 2, because then I'm solving for x. So I'm going to multiply both sides by 2 on both equations so that I can isolate my x. X is going to equal to 2 pi over 3 plus 4 pi k. And x is equal to 10 pi over 3 plus 4 pi k. Now, those are the general solutions. Those are the solutions for all real numbers, not just in the interval. But I want only the solutions that land within that interval. So if I want only the solutions that land within that interval, clearly I can't add on any multiples of 4 pi k because that's outside of that interval. Not only is 4 pi k for any value of k except for 0 outside of the interval, so is this. 10 pi over 3 is larger. 10 pi over 3 is larger than 2 pi. Because 10 pi over 3 is larger than 2 pi, that is not part of the solution either. So my only solution is x is equal to 2 pi over 3. That's my only solution. Let's take a look at the next example. So I'm just going to erase this because I need the space. My next example is when the tangent of x, the tangent of 4x, the tangent of my angle is equal to 0. It tells me I want my y value to equal 0. So that happens when I am either at 0 or at pi. So I know when it's pi k, multiples of pi k. And again, I can do this with 2. I can write it as 0 plus pi k and pi plus pi k. But I'm just going to use 1 because I can combine them. As before, I have the angle 4x is equal to that. Not just x, but it is 4x. My previous example, I had to multiply by 2 so I can isolate the x. In this example, I'm going to need to divide by 4. That gives me x is equal to pi over 4k. Now I want particular, not the general. So I'm going to say, well, what happens when k is equal to 0? When k equals 0, my solution is 0. When k is equal to 1, my solution is pi over 4. When k is equal to 2, I end up with 2 pi over 4, which we know happens to be pi over 2. However, pi over 2 is not going to give me 0. But when I put pi over 2 in right there, because I am multiplying by 4, I'm good. When k is equal to 3, I'm going to have 3 pi over 4. When k is equal to 4, I'm going to get pi. When k is equal to 5, I'm going to get 5 pi over 4. When k is equal to 6, I'm going to get 6 pi over 4, which is 3 pi over 2. When k is equal to 7, I'm going to get 7 pi over 4, and I have finally exhausted my solutions. I have 1, 2, 3, 4, 5, 6, 7, and 8 solutions. And I kind of expected that, so I'm going to give you a little heads up. When I started out and I said the tangent of 4x is equal to 0, well, on the unit circle, that happens twice. The fact that I have a 4 there, that means I take all of my solutions, which are 2, and multiply it by 4 to get the total number of solutions. With tangent, cosecant, secant, and cotangent, you do have to make sure that none of these are extraneous solutions. So you'd have to make sure that none of these are extraneous solutions. And what I mean by extraneous solutions is I'd go back and check the tangent of 4 times 0 does indeed equal 0. The tangent of 4 times pi over 4, well, this is the tangent of pi, so we're good at 0. And I'd have to make sure that none of these are going to be undefined. So be careful with tangent. They're one of the ones in which you have to confirm that you don't have extraneous solutions, because sometimes you'll get solutions, but they're not true solutions. Let's take a look at another example. We're going to do a bunch of these. On this next example, we're going to look for the sine of alpha is equal to negative square root of 3. So I would need to isolate first, so I'm going to divide both sides by 2. And I get the sine of alpha is equal to negative square root of 3 over 2. So alpha is equal to, again, I'm going to get out my unit circle. I'm going to find to see where the sine of alpha is equal to the negative square root of 3 over 2. And so I know on my unit circle that happens when we are at 4 pi over 3 and 5 pi over 3. 4 pi over 3 plus 2 pi k. And when alpha is equal to 5 pi over 3 plus 2 pi k. When k is equal to 0 is the only solution, because if I add any multiple of 2 pi k, I'm clearly going to be outside that interval from 0 to 2 pi. So these are my two solutions. So for D and E, I have a couple of steps I have to do. So the first step I'm going to do is I'm going to subtract 1 from both sides. I have 2 the sine of 2x is equal to negative 1. Then I'm going to divide by 2 from both sides. Not on the angle part, but the multiplier up front of sine. So I have the sine of 2x is equal to negative 1/2. As before, I'm going to set 2x equal to the angle equal to 2x being the angle. I go on my unit circle. Where do I get negative 1/2? Again, if you're not certain, your unit circle is your new best friend. And you can see where I have the negative 1/2 is going to be at 7 pi over 6 and 11 pi over 6. So 7 pi over 6 plus 2 pi k. And when x is equal to 2x is equal to 11 pi over 6 plus 2 pi k. Unlike my previous example when I had a singular angle and it only worked when k was equal to 0, that's not going to hold true here. So I need to divide everything by 2, which is the same thing as multiplying by 1/2. So I get x is equal to 7 pi over 12 plus pi k. And x is equal to 11 pi over 12 plus pi k. Now I have to go through the motions of finding all the solutions when k equals 0, 1, 2, 3, and up. So I'm going to take this term and have a common denominator, which needs to be 12. It'll just make it easier to find the solutions. So 7 pi over 12 plus 12 pi k over 12, which is the same thing as pi k. And x is equal to 11 pi over 12 plus 12 pi k over 12. When k equals 0, I'm going to get x is equal to 7 pi over 2. When k is equal to 1, I'm going to have 12 pi plus 7 pi, which gives me 19 pi over 12, which is still in the interval between 0 and 2 pi. So here's 2 of my solutions. When k is equal to 0 for this one, I get x is equal to 11 pi over 12. When k is equal to 1, I'm going to get 12 plus 11, which is 23 pi over 12. And here's my second set of solutions. And I expected 4 solutions because this multiplier here is 2. If I didn't have that multiplier, I knew that I had 2 places on the unit circle. That makes it true. So what that 2 does is it takes 2 solutions and produces 4 solutions. Go ahead and take a look at my next example. My next example, I'm going to have to add the 3 and multiply and then divide by the square root of 3. So the cotangent of x over 3 is equal to 3 divided by the square root of 3. So my x over 3, now cotangent and tangent, are both periods of pi, so I can make a single. I'm looking for the square root of 3 over 3. I'm just going to rationalize this because I remember the rationalized part, which is 3 times the square root of 3 over 3, which is just the square root of 3. Now the reason I do that is because I know that the tangent of an angle is the square root of 3 when I'm at pi over 3. That means the cotangent must be true when I have pi over 6 plus pi k. So in other words, 30 degrees. As before, I'm going to multiply everything by 3. And so I end up with x is equal to 3 pi over 6 plus 3 pi k. So x is equal to pi over 2. Now, I don't have to worry about this one, unlike my previous one when I go through the iterations, have the same common denominator and all that, because I know that if I'm adding 3 pi k, that is more than the interval between 0 and 2 pi. So I know I don't really have to pay attention to that part of it. So my only solution is just pi over 2. Now I just got to make sure that when I put pi over 2 back in here, it does not produce a value that is undefined. My next example, this looks kind of like a quadratic. If I say let u equal the cosine of beta, then what I have is u squared is equal to the cosine squared of beta. That means 2u squared is equal to -1 minus 3u. Oh, that's a quadratic. So 2u squared plus 3u plus 1 is equal to 0. Nice, easy factoring. So I go to factor this thing and I say, oh, this is 2u plus 1, and this is u plus 1 is equal to 0. So I get u is equal to -1/2, and I get u is equal to -1. Now, I am not solving for u, I'm solving for the cosine of beta. The cosine of beta is equal to -1/2, and the cosine of beta is equal to -1. Now, by this point, you should see that when I have a singular angle, it's not necessary to add that plus 2 pi k. You can, absolutely, but it is necessary when my angle is not a singular beta. It's like 2 beta or beta divided by 2. That's the time I have to do that. So I'm just going to go out to my unit circle, and I'm going to say, well, where is my angle? When I take the cosine of my angle, where is it equal to -1/2? That's in quadrant number 2 and quadrant number 3. So when I'm at 2 pi over 3 and when I'm at 4 pi over 3. Again, I can put the plus 2 pi k, right? I can always do the plus 2 pi k, but I know that since I have to stay in the interval between 0 and 2 pi, in this case, it really makes no difference to add that. It's not going to give me anything. Now, when cosine beta is equal to 1, this only happens when I'm at pi, and that's it. So I end up with 3 solutions. And I approach this as if it was a quadratic. And I was able to approach this as a quadratic because I have the same angles. If that was beta and 2 beta, I would not be able to do that. But because it is just beta, I can treat it as a quadratic. Now, we would be tempted to say the tangent of x, the sine of 2x is equal to 0, and say, wait a minute, I know what the sine of 2x is. So the tangent of x, the sine is the double angle, so it's 2. The is sine x cosine of x is equal to 0. And you're like, wait a minute, we have the tangent of x is the sine of x over the cosine of x. And we get so excited. We have the sine of x over the cosine of x multiplied by 2, multiplied by the sine of x, multiplied by the cosine of x is equal to 0. And you're like, oh, cool. These cancel. And I end up with 2, the sine squared of x is equal to 0. I divide both sides by 2, and I get the sine squared of x is equal to 0. Take the square root, and so I'm really just chasing when the sine is equal to 0. Now here's the problem. You eliminated a solution. Sure, you have the identities that allow you to do that, but when you do that, you have lost a solution. This is more like of the form u multiplied by v is equal to 0. That means that u is equal to 0 or v is equal to 0 or both. So what I really have is the tangent of x is equal to 0 and the sine of 2x is equal to 0. So I know the tangent is equal to 0 when x is at 0 and when x is at pi. Cool. And then I have the 2x. Sine is equal to 0 in the same places, which is 0 plus 2 pi k. And 2x is equal to pi plus 2 pi k. As before, I can truly indeed combine these, so I will. And so I'm going to write this as just 2x is equal to pi k. Because they're off from each other a distance of pi. A rotation of pi. So x is equal to pi over 2k. So I have to go through the iterations. So k equals 0. X is equal to pi over 2. When k is equal to 1, when k is equal to 0, I get 0. When k is equal to 1, I get pi over 2. When k is equal to 3, I get, oh, I dropped 2. Look at that. Didn't think I needed 2. When k is equal to 2, I'm going to get pi. When k is equal to 3, I'm going to get 3 pi over 2. Now, had I done exactly what I started out with, if you remember before I erased, I ended up with the sine of x is equal to 0. When I did that, my only solutions are 0 and pi. I dropped this solution and that solution. So just because you can simplify with identities, sometimes it's best you don't simplify with identities. My next example, I will simplify with identities, but my first example, if you did, you lost 2 solutions. You lost the pi halves and you lost the 3 pi over 2. So be careful that you're not going to just necessarily just jump right in and find solutions. Sometimes you're going to have to do a little bit of work first and not use identities. Now the problem with this one is I see I have an angle of 2x, an angle of x, angle of x, angle of x. So this one I do have to use an identity. I'm going to replace sine 2x with 2 the sine x cosine of x. And then I still have the minus the sine of x, the cosine of x, and this still equals the cosine of x. Once again, I am not going to divide everything by cosine x because when I do that, I'm going to lose a solution. But I absolutely can combine these two up. When I do that, I'm going to get the sine of x, cosine of x, is equal to the cosine of x. Again, I am not going to divide each side by the cosine of x because I am losing a solution every time I do that. So what I will do is move the cosine of x to the left-hand side. Sine of x, cosine of x, minus the cosine of x is equal to 0. Now I'm going to factor out the cosine of x. Cosine of x, the sine of x minus 1 is equal to 0. That means from here I get the cosine of x is equal to 0, and I get the sine minus 1 is equal to 0. From that one. So this one gives me solutions of pi over 2 and 3 pi over 2. This one is the sine of x is equal to 1, so x is equal to pi over 2. if I would have divided everything by the cosine of x, if I would have divided each term by the cosine of x, I actually would have lost that solution. So just because you can doesn't mean you should. Let's take a look at another example. In this example, I have the sine of 2 theta. The problem is, again, that these angles don't line up, so I'm going to replace the sine of 2 theta with the 2 the sine theta, the cosine of theta, is equal to 3 the sine theta. Once again, I'm going to move the sine over to the other side because I am not going to divide by sine. I lose solutions. 2 the sine theta, cosine theta, minus 3 the sine theta is equal to 0. I'm going to factor out a sine theta. So I factor out a sine theta, and I have 2 the cosine of theta minus 3 is equal to 0. This tells me that the sine of theta is equal to 0. And this gives me the cosine of theta is equal to 3 over 2. This tells me that theta is equal to 0 and pi. And this tells me that this is no solution for this part. This is extraneous because you can't have the cosine of an angle be larger than 1 or less than negative 1. So even though we got an answer, sort of, we don't get an answer. The only solutions are these. All right, so I have the tangent squared sigma minus the cosine squared sigma. Now the problem that I have is I have tangent and cotangent. So if I have tangent and cotangent, and I have a mix, I'm going to have to write it as a single one. So I'm going to write the tangent squared of sigma minus 1 over the tangent squared of sigma is equal to 0. Now I have everything in terms of tangent. I'm going to go ahead and make this a single fraction, and so I'm going to multiply this term by the tangent squared sigma over the tangent squared of sigma, so I can have a common denominator. So I'm going to get the tangent to the 4th sigma minus 1 over the tangent squared sigma, that looks like an alpha, sigma is equal to 0. Now I happen to know that that is never going to be 0 because it's in the denominator. So that won't even be a part of the solution. This is like looking at rational equations. When you're solving rational equations, your denominator is not going to be part of the solution. It can tell you where you might have restrictions, but it's not going to tell you what your solutions are. So we only work with the numerator. So we have the tangent to the 4th sigma minus 1 is equal to 0. So the tangent to the 4th sigma is equal to 1. I'm going to take the 4th root of both sides. When I take the 4th root of the right-hand side, don't forget the plus and minus. So I'm looking for the tangent of sigma, which is equal to plus and minus 1. This happens when sigma is pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Those are the locations in which tangent is equal to either 1 or negative 1. All right, so let's look at my next example here. Again, this kind of looks like a quadratic, so let's let u equal the sine of alpha. This is a reducible quadratic, so this is a nice refresher for your pre-calculus 1. U squared then would be the sine squared of alpha. So then what I really have is u squared plus 9 is equal to 6u. U squared minus 6u plus 9 is equal to 0. U minus 3, u minus 3, u is equal to 3. Not solving for u, we're solving for the sine of alpha, which is 3. Oh, no solution. Because we know the ratio for sine has to be between negative 1 and 1. So that's also a no solution. We take a look at this example, and now this thing looks a whole lot like the difference of alpha, tangent of alpha minus beta. So this left side looks like the tangent of 3 beta minus beta. Then this equals the square root of 3. So it looked like something awful, but if we can recognize that that is an identity, then what we really are looking for is the tangent of 2 beta is equal to the square root of 3. So in other words, we're looking for 2 beta is equal to the angle that produces square root of 3, which is pi over 3 plus pi k. I can also do the 4 pi over 3, but remember they're off by a difference of pi, so I'm just going to do pi over 3. As before, I'm going to divide everything by 2, in other words, multiplying by 1/2. So I have beta is equal to pi over 6 plus pi k divided by 2. And since I have to go through the iterations of k, I'm going to go ahead and make the common denominator for this part, so this term. So I'll go ahead and multiply the numerator and denominator by 3. So beta is equal to pi over 6 plus 3 pi k divided by 6. When k equals 0, beta is equal to pi over 6. When k is equal to 1, it's going to be 4 pi over 6, 4 pi over 6, which reduces to 2 pi over 3. When k is equal to 3, why do I keep missing 2? I don't know. Maybe 2 is not my friend today. When k is equal to 2, and I have 2 times 3, which is 6, plus 1 more is 7, 7 pi over 6. When k is equal to 3, I'm going to have 3 times 3, which is 9, plus 1 more is 10, so 10 pi over 6, which does reduce to 5 pi over 3. When k is equal to 4, I'm going to end up with 13 pi over 6, but that does not belong in the interval between 0 and 2 pi. That is not in there. So I don't get to have that one. So the only solutions I have, which are still quite a bit, is pi over 6, pi over 4, or excuse me, pi over 3, because I want to use the reduced form, pi over 7 pi over 6, and 5 pi over 3. A couple of more examples here. Okay, this is still a reducible to quadratic, so this is still a nice pre-calculus 1 review. We're going to let u equal the cosine squared of theta. That means u squared is equal to the cosine to the 4th of theta, which means I really have 8u squared minus 10u plus 3 is equal to 0. So that's still a quadratic. It's reducible to a quadratic, so I will reduce it to a quadratic. And I'm looking for factors of 8 and 3. When I multiply them together as a combination, I'm going to add up to 10. So I'm going to use 3 and 2 and u and minus and minus. And I'm just going to check that these two give me 6, these two give me 4, so those are my combinations. Cool, 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 cool. So I end up with u is equal to 3 over 4, and I get u is equal to 1/2. However, what I really have is the cosine squared of theta is equal to 3 over 4, and the cosine squared of theta is equal to 1/2. As before, I do need to take the square root of both sides, and I need to make sure I put on the plus and minus. Don't forget that. The square root of this, the square root of this, plus and minus, square root of this, square root of this, plus and minus. And so I'm going to get the cosine of theta is equal to plus and minus the square root of 3 over 2, because I'm going to rationalize the numerator and denominator separately. And I'm also going to get the cosine of theta is plus and minus. I'm going to rationalize this and get the square root of 2 over 2. This one is going to give me pi over 6. It gives me a positive one. 5 pi over 6. There's a negative one. 7 pi over 6. There's a negative one. 11 pi over 6. There's the positive one. So all of these come from this one. Here, I'm going to get theta is equal to pi over 4. There's a positive. 3 pi over 4. There's a negative. 5 pi over 4, there's another negative, and then 7 pi over 4, here's the other positive. all of these come from this one. So if you get this one wrong, I bet it's because you forgot to slap on that plus and minus. One more example, and then we're going to put it to bed, and this is going to be similar. We're going to let u equal to the cotangent squared of beta. U squared is going to be the cotangent to the fourth of beta. That means that I have u to the fourth minus 4u, that should be u to the squared, minus 4u plus 3 is equal to 0. That means u minus 3, u minus 1 is equal to 0. U is equal to 3, u is equal to 1. Cotangent squared of beta is equal to 3. The cotangent squared of beta is equal to 1. Do not forget when you do the square root of both sides that you remember that plus and minus in the appropriate location. So the cotangent of beta is equal to plus and minus the square root of 3. This happens when beta is equal to pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Cotangent of beta is equal to plus and minus 1. This happens when beta is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Do not forget that plus and minus, or you have lost half of your solutions, which means you would get 50% on this because you have lost half of your solutions. 50% is not passing. All right, so now we are going to solve the inequalities. We want to know where the tangent of x, the outputs for the tangent of x, is greater than the square root of 3. So, once again, I'm going to go out to my unit circle. There are a couple of solutions. We want it to be greater than or equal to. In this region, from here, inclusive but non-inclusive at pi over 2, this is a region in which the tangent of x is going to be at least the square root of 3 and no larger. Once I get into this quadrant, my tangents will be negative numbers. So my first solution is when we are at pi over 3 inclusive, pi over 3 inclusive, and then it stops at pi over 2 non-inclusive because you can't have the tangent of pi over 2. The other location in which I have the square root, positive square root of 3 is down here in this quadrant. Once I get into the next quadrant, my tangents are negative numbers. So then this is going to union with 4 pi over 3, and then all the way to 3 pi over 2, but non-inclusive because you don't get to include 3 pi over 2. Sine is less than 0. Well, where is the location of sine being a negative number on the unit circle or equal to 0? The location where sine is negative is in this quadrant and this quadrant. So the solution here is between pi and 2 pi. Non-inclusive because you don't get to include it up here. That's all. Here's the next one. I want to know where the cosine squared is greater than 1/2. So what I'm really looking to solve is where the cosine squared of x is equal to 1/2. So I'm really looking to solve is where cosine is equal to plus and minus the square root of 2 over 2. So I'm really trying to find out where the cosine has a ratio bigger than the square root of 2 over 2. And it's positive. And it also has to be the negative part. So we want to know where, when I square this, it is strictly greater than that. In this region right here, cosine in that region, when I take any ratio of an angle in that region, When I square it, it'll be bigger than 1/2. So that region will be a solution, not inclusive of the pi force. So between 0 and pi force, inclusive of 0 and non-inclusive of pi force, because I don't get inclusive here. The other location is right here. So this is another location in which when I take and square any ratio in that region, so when I square any ratio in that interval of angles, I will also have a number that is bigger than 1/2. So non-inclusive of 3 pi over 4, because it has to be strictly greater than, and then all the way to pi. However, I can continue on into this quadrant as well. So this quadrant isn't going to stop at pi. This quadrant is going to continue all the way to 5 pi over 4. Now here I'm going to put a parenthesis because I don't get to include where it's equal to when I square it, equal to 1/2, because this is non-inclusive. And the very last location is this quadrant. So then I add that last one on, which is 7 pi over 4, all the way to 2 pi, non-inclusive because of my interval right there. All right. Let's take a look at our last one. We have the sine of x minus pi thirds has to be greater than 1/2. So as before, I have x plus pi thirds. I'm going to look for the interval in which I am bigger than 1/2. I'm going to go back up to my unit circle, and the interval in which I am bigger than 1/2 is positive pi 6 all the way to 5 pi over 6. So this will be true from pi over 6 all the way to 5 pi over 6. Now, what does this plus pi thirds do? Well, plus pi thirds picks up my sine wave and it moves it to the left. Now, if I were to graph my sine wave, my regular sine wave, it would look something like this, right? I would have this interval from pi 6th to 5 pi over 6. These values right here are above, non-inclusive, but above, though not including those endpoints, are outputs that are bigger than 1/2. If I have x plus pi thirds, that means this is going to get shifted over pi thirds, and so is this. The entire graph, the sine of x minus x plus pi thirds, the sine of x plus pi thirds, picks this entire interval up and this entire sine wave and moves it left. So I have pi over 6 minus pi thirds. So that means this is going to go to negative pi 6. Because this point is going to move here to pi thirds. This point is going to move back. This point is going to move back. So negative pi 6 is my interval. So this is going to go to the interval, negative pi 6. I also have to do 5 pi over 6, and I need to subtract off that pi thirds because I am moving left. That gives me 3, that's 2 pi over 6, so that gives me 3 pi over 6, which is pi over 2. So my sine wave has moved. It looks like this now. So starting at negative pi 6 and ending at pi halves, so wherever pi halves is. So from here to here, there's my movement. So from pi halves to negative pi 6 to pi halves is the solution for this, so pi halves. So you can still solve the inequalities even with a phase shift. Now we have seen example after example after example of right triangle geometry or trigonometry. Now here's examples in which the entire time we were doing that, we were solving equations. We were solving trig equations. So let's just solve a couple of these trig equations. If a loading ramp is placed next to a truck with a height of 2 feet, So here's 2 feet with a ramp of 20 feet long. 20 feet. What angle does the ramp make with the ground? So what we're really asked to do is find not the tangent, but the sine, because I have the y value and the r value. So the sine of theta is equal to 2 over 20. Now it doesn't tell me which one to do this with in terms of sine or cosine in terms of degrees or radians. So I'm going to use degrees because it would make more sense to tell somebody the answer in degrees. So again, this time I'm going to take the sine inverse. So I'm going to take the sine inverse of 2 divided by 20, because that's not one on my unit circle. And so my angle is, and it's only one, which is 5.74 degrees. Here's an example in which we are solving. This is solve an equation, but it's not on the unit circle. Spotlight on the ground 3 feet from a 5-foot tall woman. Here's my light. Here's my person. Cast a shadow 15 foot long on a wall 6 feet from the woman. So we know this is 3 feet. We know this is 6 feet. We know the shadow is 15 feet tall. We also know if we don't cut her head off there with my perfect drawing, I know you're like, oh my God, you do the best, people. Your drawings are like the best. Now the person looks like they got a super long neck. Let's try this again. There we go. This person is 5 feet tall. Okay, we want to know the angle of a spotlight. Cast a shadow, 15-foot shadow 6 feet from the woman. What is the angle of the shadow? Oh, sorry, what is the angle of the light? So this is theta. So I could use one of two ways of doing it. I'm going to use tangent. So I could say the tangent of theta would be 5 over 3. Or I can say the tangent of theta is equal to 15 over 9. It's the same ratio. It doesn't matter which one. And again, I am going to use my calculator. I'm going to give the answer in degrees because it makes sense to do it in degrees. So I'm going to do the tangent inverse of 5 divided by 3. And I get my theta is equal to 59.03 degrees. And that's it for this section. So some of the stuff that we've been doing this for a while. In fact, these last two examples, we already did these. We did this in right triangle stuff before, and we also have, at this point, learned the law of sines and cosines. So there you have it. That's it for this section.